Thank you for the introduction. And my research interest is in symplectic geometry. So the most used vocabulary for me is contact manifold and symplectic manifold. So a contact manifold is an odd-dimensional manifold with a hyperplane distribution C such that it's completely non-integrable. That means it's very twisted. In particular, it's a complete opposite of this coming from affiliation. So the major example of contact manifold are like basic examples are like a Euclidean space with a contact distribution given by the kernel of that one form. That one form is called contact form. And for a sphere, we also have a contact distribution given by the tangent and it intersects the tangent when you rotate it by the complex structure from Cn. And another family of examples is like the sphere bundle of the cotangent bundle and the links of singularities. So the first one is kind of similar to this one, and this is similar to this one, the contact structure is given.
All right, before you move on, can you explain this C standard again? So at every point, the affiliation
is given by, so you have this sphere embedded in Cn, and you have a tangent space, and then you multiply your tangent space by the complex structure, intersect with your tangent space. You get a hyperplane distribution.
I'm so slow. That thing is a hyperplane?
Yes, this is a tangent space, and you rotate by the multiply the complex structure I. You get another like dimension 2n minus 1 in the Cn, and intersect them. You get a codimension 1 in the tangent space of the sphere. The link one is similar. Okay, so if you Google it, the contact manifold, what you will see is a picture like this. This is the contact distribution on R3. You see how things are twisted. Okay. And why we study contact geometry is it's a natural notation of boundaries of symplectic manifold. So symplectic manifold is an even-dimensional manifold with a two form which is non-degenerate. So in this case, I'm interested in studying the Liouville fillings, also called exact fillings of contact manifold. So basically, you have these structures. First, the contact form is given by the kernel of this one form, and the exterior differential is a symplectic form on it. And the other thing is you have a vector field pointing out along boundary such that this relation holds. So this relation means the symplectic form is a derivative along this vector field of symplectic form is symplectic form itself. That means symplectic form is like growing exponentially. So what we typically draw is like this. And that's my y, and I have a vector field here indicating it's growing exponentially. Okay, so that's a filling. And the standard example is if we take the standard ball, that's a filling of the standard sphere, and the cotangent disk bundle is a filling of the sphere bundle. And if you take a singularity, if you can smooth it, it will be a filling of the link of the singularity. And we can similarly talk about so-called cobordism, which is you have kind of two boundaries. And one direction, this vector field is pointing out. The other direction is the vector point. This vector field is pointing in. So it's one convex boundary, one concave boundary. That's called the symplectic cobordism. And one basic question is we want to understand this category. Okay? But this category is very different from topological one. First of all, you cannot invert it. If you have a cobordism from y1 to y2, there's no cobordism from y2 to y1 if you assume it's exact. And also, even if you remember all the topological information, it's still very different. So something about symplectic geometry is going on here. So the question I want to understand is understand this category. Okay, so what are the tools we have? So there's a tool which is very suitable for the study of this cobordism, which is called symplectic field theory, introduced by Eliashberg, Giventhal, and Hofer, I think 20 years ago. So it's a field theory, meaning that for this cobordism, meaning that for every y, you assign some algebraic object. It's called Asymptotic. And for every cobordism, you have a map which is from the Asymptotic 2 to SFT Y1. So this makes it suitable to study in this category. And there's a special case I'm going to very interesting is called the contact homology. It basically is assign algebra to every contact manifold and algebra map. It's actually differential graded algebra if you assume some actual condition for cobolism. And there's a special case for the algebra is if you consider contact manifold to be empty set, the algebra is a ground field. So in particular, if you have a filling that will give you a map from the contact homology to the ground field, and this is called augmentation. And you can think of augmentation as an algebraic analog of filling. And the point is, classify this is much easier than classifying fillings, right? So the slogan I want to talk about is, if the contact manifold admits only trivial augmentation, you always have one trivial augmentation, assuming something. That is, because this guy carries a copy of the ground field, you just send everything to 0, send that ground field to the ground field that is called trivial augmentation. It exists in some cases. Some cases it's not augmentation. Okay, and I want to say that in this case, many Floer-theoretic property and topological property of the filling is actually independent filling. The dream is proving there's only one filling, but we can only achieve like some information about the filling. Okay, so I will introduce one concept which will guarantee that there's only one trivial augmentation, which is called the asymptotically dynamically convex, which is a concept introduced by Oleg Lazarev. So the takeaway is basically if it's ADC, then the SFT grading is positive. So there's no augmentation by degree reasons, non-trivial. So you have no. And the interesting thing about this property is preserved under certain construction in symplectic geometry called the subcritical and flexible handle attachment. So this gives us tons of examples. The first one is boundary of flexible Wien-San domains. I will explain a little bit later, so which is based on his theory. And second class is the unique sphere bundle of the cotangent bundle when the dimension is bigger than 4. And the last one is the results of Mark McLean, which says the length of terminal singularity is ADC. It's actually if and only if. Okay. So these are the. So what do we know about the uniqueness of symplectic filling? So first of all, a classical result by Alasheper, Floer, Makdorf is showing the exact fillings of the standard sphere are diffeomorphic to a ball. In dimension 3, it's actually symplectic. You can recover the symplectic information as well. And this method was later generalized by Wang-Sharf-Turbo, Bar-Skegel-Stemisch to the following, which says simply connected subcritically fillable contact manifold of dimension bigger than 5. The exact filling has unique diffeomorphism type. Oh, this is a special case because this guy has a filling which is a ball, which is also subcritical. So subcritical basically means the filling you build, you can put a Morse function there compatible with the symplectic structure, and the index is strictly smaller than half. Okay. So the method they use is using holomorphic curve theory, and they're trying to find the foliation of the filling. And why there is a foliation is because if you have W is subcritical, then it actually split into a product. So that's why you have the foliation direction. So that's why their methods how their methods work. And what I'm going to talk about is very different from their approach. So actually, this doesn't fit into the SFT thing I just told you. So what I want to use is a different property of the contact manifold, which I just introduced, the ADC condition. So I'm going to use Floer theory to study this question. So the Floer theory I use is something called the symplectic cohomology, which assigns for every Liouville domain like 2 Floer series, which is called SH and SH plus. And they fit into this long exact sequence. So this has a close relation to SFT. And the benefit of this is it's well defined. So SFT is the construction SFT is a huge project which is still ongoing, but I think it's close to finish. And the other thing is this is way easier to compute and easier to understand. SFT is an enormous algebra. It's super hard to work with. So what I proved in summer is the following. If Y is ADC, then this map, where the first map is from SH plus to the filling, and you restrict to boundary, is independent of filling when you have these two topological conditions. So here C1 is important because I'm using asafety grading. This is related to grading. This, maybe you can forget about this. And the point here is I only assume filling. So actually you can work with strong filling, like non-exact fillings. Okay, so what are the corollaries about this result? So first of all, this SH symplectic homology is a ring, and this map is a ring map. So 1 inside this image is equivalent to this is 0. Okay, so this shows the vanishing of symplectic homology as a property independent of filling. And as a consequence, I can show that if Y is flexible fillable, which is ADC, then this restriction map is independent of filling, because when it's flexible, the symplectic homology, one filling has vanishes symplectic homology. So all of them are independent. And this is essentially the topological information you need to get the diffeomorphism type, because they use H cobordism argument. Actually, you verify some homology information. So this will actually give you the uniqueness of diffeomorphism type for some examples. Okay, so this is, so as I said, a quick corollary is vanishing of symplectic homology as a property independent of the filling. And the other thing is the vanishing of symplectic homology is actually the first property in a whole sequence. And the next one is called something called dilation, which has something to do with S1 action on the loops. And we have a BV operator. We say it has a dilation if there's an element in degree 1, so that BV operator hit on it, you have 1. And similarly, this is introduced by Seidel and Solomon. And we can similarly define generalization of this, which says, because if we consider S1 equivalent series, there's a U spectral sequence, and vanishing means one vanish in the first page, and dilation means it vanishes in the second page. I can define a similar thing for all K. And the point is there are some maps related to this structure, and all of them are independent of filling if the boundary is ADC. Okay. And so a quick corollary of it is the existence of K dilation is a property of independent fillings if the boundary is ADC. And another thing is if Y is ADC, then this map, which is the first structure map, very simple here, is independent filling. But this map factors through the middle cohomology. So if this map, the image of this map contains something above the half dimension, that means the filling cannot be a Weinstein filling. So it provides you obstruction of Weinstein fillings. So Weinstein means you have a handle body decomposition of the filling up to like index at most half. Okay. At this point, it looks like I'm using the topology of the filling, but the point is this guy is not topological. So in fact, I find the infinite Manet 4K plus 3 contact manifolds that are exactly fillable, almost Weinstein fillable, but not Weinstein fillable. Almost Weinstein fillable means there's no topological obstruction. Okay. Okay. And another thing is this K dilation is actually the hierarchy. If you have K dilation, it automatically has K plus 1 dilation. And if you have a embedding like this, if the outside one has a dilation, K dilation, the inside one must have a K dilation. So this can be used to understand this category of cobordisms when the boundary is ADC, because the boundary ADC means I can forget about the filling. Okay, so they can use to define cobordism obstructions for ADC manifold. Okay. Yeah.
Can I ask for these non-Weinstein fillables, how simple can you make the topology of Y? For example, can you make Y be like a sphere even?
No. So the example is we should start with some Liouville domain which are not Weinstein. Unfortunately, there are only one construction right now. So what I take is I take that and I multiply it by a huge copy of C, and then I attach a flexible handle. But I don't think the topology of the boundary is so very simple. Yeah. Because the problem is check that's almost Weinstein fillable. So that problem, we know that it's reduced to computing some Bordism group, except the Bordism group is extremely hard to compute. So
why do you attach the flexible handle?
I want to verify that the theory, like Boltzmann theory, vanishes to like kill certain homology, homotopy group.
Well, I mean, why not just multiply by the CN?
It's also not Weinstein fillable, but it's I don't know whether it's almost Weinstein fillable or not.
Oh,
Yeah.
Okay.
Yeah. So if you only want a not Weinstein fillable, it's super easy. You just take one and do whatever. It's still okay. So the future questions I want to understand here is trying to reformulate this construction using SFT. I'm using the easy technique called symplectic homology, but if you use SFT, potentially you can get a much stronger result of it. So that is after the SFT is complete. And second thing is this existence of K dilation implies unirule, meaning that this passing through every point, you have a holomorphic curve. And but it's very unlikely that this unirule will imply the existence of K dilation. But as showed by Mark McLean, the unirule for symplectic manifold for affine variety is actually a symplectic notation. So I'm wondering if there is a characterization of uniruleness of affine variety using Floer theory. And the last part is this K dilation is trying to give you a very coarse classification of this manifold with very rich holomorphic curve. Or actually, if you are working with affine variety, this is in the part where your log quadratic dimension is negative infinity. So there are also a huge amount of varieties after that. So what can we do about that? Maybe we can do something about log quadratic dimension is 0 because there are still holomorphic curve, but not so many. But after that, maybe the current technique will break down. So I want to end this talk with my understanding of this Boltzmann category by picture. So this is our from here, this is Boltzmann category. So first you have something without filling. That's called the over-twisted. That's first discovered by Ali Ashberg, and then in higher dimension generalized by Bowman, Ali Ashberg, and Murphy. And then we have something called Giroux torsion. It's like I don't know, it's not generalization, but something below that. And then there's a notion called K torsion, which you can think of over-twisted as 0 torsion, Giroux torsion is 1 torsion, and here you have all these K torsion. But all of them are without filling. And it's kind of the minimum element. Over-twisted is actually minimum element in this category. And then we start with something with fillings. So, but the filling might be unique. So we have this flexible fillable. And so, for example, the sphere is an example. And then we have this vanishing of symplectic homology. And then we have symplectic dilation and K dilation. But this is still in the region of log quadratic negative. And then we enter into maybe less holomorphic curve, so maybe log Calabi-Yau. And there's a notion of quasi-dilation, and there is also a notion quasi-cyclic dilation introduced by Ying Li recently. And the essential example seems to live in the log Calabi-Yau case. And later we have positive and then maybe general. But later we have all the examples with maybe infinity fillings. But can we say something more structured results for these things? And after that, we don't know what's going on. But the good news is there's a happy place after everything is if you complete everything down to the very end, we will get an empty set. That's a happy ending for us. So it's actually a result for every contact manifold. You have a capping, which is composite from to empty set. But the is not exact. Okay, but hopefully we can understand everything before that and get to this happy place. Okay, thank you.